let's prove a special case of this number theoretic result. P equals 5 is a prime number. Okay, now if we take a look at what this is trying to show us, we need to sum up the first p minus 1 squares. Okay, so just right above this, I'll write down 1 squared plus 2 squared plus 3 squared plus 4 squared. Okay, so what do we get here, y'all? This is 16, this is 9, 16, 9 is 25. This is equal to 30. Now notice that 30 is certainly congruent to 0 mod 5. Another way to state this is that you see this vertical bar notation gets used quite a bit. 5 vertical bar 30. 5 divides 30 is another way of, this is absolutely equivalent to this congruence notation. Okay, now let's go ahead and prove it for the general case, and it's not surprising this result about squares would pop up. Now this is an induction proof. We're going to state it as though it's a fact, but it does require mathematical induction to establish the truth of this. I think, as far as I know, that's the only way to do it. There may be other proofs, but let's see what happens here. It's very natural here to take n equal to p minus 1. Okay, because this is true for any natural number, so a prime number minus 1 is certainly a natural number. So we're going to go ahead and just substitute n equals p minus 1 into the formula. And everything, I've written down everything that's important right down here, folks. You can see if you just put it here, p minus 1 plus 1 is just the p that you see right here. Okay? And so anyway, that's what happens when we substitute n equals p minus 1 into the result. Now, this is really fairly straightforward. Just by definition, since p is prime, 6 can't divide it. Otherwise, p wouldn't be prime, right? A prime number has only 1 in itself. As a prime number, 6 is certainly not prime. So it's clear that 6 cannot divide the prime number. So that forces the p minus 1 times 2p minus 1 to be a multiple of 6. Because remember, this is an integer right here. Remember, with the sum of the squares is equal to an integer. And so this has to be a member. I can just say that, if you want to, the natural numbers, I guess. Okay, it has to be a natural number. So that forces p minus 1 times 2p minus 1 to be a multiple of 6, since 6 has to go somewhere, right? And this is supposed to be an integer. If it doesn't divide p, it has to divide p minus 1 times 2p minus 1. Okay, it's the same thing as saying that p minus 1 times the quantity 2p minus 1 is a multiple of 6. So we can write down p minus 1. And a lot of, you could say the proof is complete right now. You can just see that it's true. But we can be a little more formal if you want. We'll say that we're just going to rewrite what we said a little more tersely. That's equal to 6m, where m is just some natural number. Okay, call that 6m. And what do? We just substitute that right here in place of p minus 1 and 2p minus 1. So we get the 6m, and it's clear that this is congruent to 0 mod p, since the 6's cancel. And p clearly, I'll just write it, it's obvious, but I'll just write down p clearly divides mp, right? Okay, so that gives us a QED on this. Now, if you want, we could just try out another one. Let's see how, I don't know how the numbers may get big kind of fast. Let's try maybe, if you want, let's try p equals to, let's say just 7, okay, 7. So let's do it for p equals 7. So what would we get for p equals 7? We would get 1 squared plus 2 squared plus 3 squared we're going to go all the way out to 6 plus 4 squared plus 5 squared plus 6 squared, 6 being 1 less than 7. Okay. So let's see here. What do we got? This is equal to, let's see, y'all. This is 5 plus 9 is 14 plus 16. We've already seen that that's equal to 30, right? We did that earlier. So that's 30. And then plus 25 plus 36. Now we're wanting this to be divisible by 7. Let's see what happens. Okay. That would be 61 plus 30. That's equal to 91. But notice that 91 is equal to 7 times 13. Okay. So 91 is indeed divisible by 7. Y'all, this gets used to prove something called Holtenstein's result, I think. It's a little more involved than this. This is kind of a preliminary result to prove Holtenstein's. But anyway, we actually proved it right here. And by the way, hopefully you can see why we have to pick the prime to be greater than or equal to 5. And that's essentially due to this formula right here. Notice that 6 itself, the constant right down here, 6 is equal to 2 times 3, and that messes up things in terms of the cancellation and so forth. So the fact that 6 is equal to 2 times 3 is why we eliminated the primes 2 and 3 and started at 5. Okay, thank you for viewing.